And I'm happy to be your host today for our suite of hyperwall talks. We have a great group of speakers today, and I'm very happy to introduce our Planetary Science Division Director, Dr. Lori Glaze.
All right, thank you. Welcome to AGU. Woo! And how awesome is it we get to kick off the hyperwall talking about all the amazing stuff going on in planetary science. So let's go. Next slide. Let's see what we got. That's not the next slide. I'll just vamp. We'll talk. There we go. All right. So planetary science program at NASA, we have so much amazing stuff going on that's exploring the entire solar system, all the way from Mercury, all the way out into the Kuiper Belt beyond Pluto. You can see here we've got about 40 missions going right now, either in operations or in development, doing amazing science to help us better understand the origin and the evolution of our solar system and where we came from. And I'm going to give you a few highlights, just a few of some of the really cool stuff going on. If we can go on to the next slide, please. Okay, next one. Next. Thank you. So this is the big one. Yes, this is the big one. All our folks over here at Johns Hopkins Applied Physics Laboratory led this mission called the Double Asteroid Redirection Test, humanity's first ever planetary defense mission to move an object in space. And so this mission, we were flying to a double asteroid. You just saw the main asteroid go out of view, and now we're targeting the smaller asteroid, Dimorphos, and we come in close, closer, 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 bam. Direct hit. We meant to do that. You're supposed to cheer. Yay. Fantastic. This is an amazing mission to, actually, as I said, planetary defense. We want to be able to, in the event that there was an asteroid headed towards Earth that could be dangerous, that would be really bad, we want to have the ability as humankind to help protect ourselves. And so this mission was a demonstration. The particular asteroid was not a threat. But we wanted to test the technique, this kinetic impactor technique, before we have a threat that we know about. So that's what we did. If we go on to the next slide, please. These are some of the images that were taken that we've been able to look at after the fact. So what you see over here on the left, this is an image taken from a ground-based telescope in South Africa. And so we're watching this as it happens. And what you see, you can see the larger asteroid go across. You can't actually see the asteroid we hit. It's too small. But you can certainly see the impact. You see the rocks get vaporized and thrown off of the surface of the asteroid. And then over here on the right, you can see these are images taken by a small CubeSat that was flying along with the main spacecraft. This little CubeSat was built by the Italian Space Agency. It's called Licia Cube. And these are images, this is an image that was taken right at that time of impact. And what you can see, it's been contrast enhanced so that you can actually see the fine structure in that ejecta, the rocks being blown off of the surface. Absolutely spectacular. We're going to be studying this for some time to come. If you can go on to the next slide, please. Oh, let's go back to the other one. I don't have my comment on here. The whole objective of this mission, of course, is to change the orbital period of the smaller asteroid around the bigger one. And we had such a good effective hit with the spacecraft that we changed that orbital period by 30 minutes, about 32 minutes. The orbit was around 12 hours, and we changed it by 32 minutes. So if we knew far enough in advance that there was an asteroid that was going to be a threat to Earth, if we knew far enough in advance, we could send a spacecraft out there, use this technique, change that orbital period so that when it crosses over Earth's orbit, we're not there. We've already gone by, and it can come by without harming Earth. So that's the whole point of this mission, and really successful. Go on to the next slide, please. So the other big thing I wanted to talk about here that's been going on in planetary science, you may have heard we have a rover on Mars. We actually have a couple rovers on Mars. But Perseverance has been on the surface of Mars almost for 2 years. It'll be 2 years in February. And the Perseverance rover is exploring a place on Mars called Jezero Crater. And we went to Jezero Crater because it's really important geologically on Mars. It's been around for about 3.5 billion years. And what you can see here, what's really cool, is all of these deposits. It looks like sedimentary deposits, and in fact it is. We know there was a lake that was present on Mars for a long period of time within this crater. And what we want to do is study the crater floor and understand this, what you see, the front of a river delta where water flowed into that standing body of water in the crater. If we could go to the next slide, please. So I just love to show this picture here. This just shows, this is proof there's aliens on Mars, and those aliens came from Earth. This is our back shell in the parachute from when Perseverance landed on Mars. I just love that picture. If we can go on to the next slide, please. So the main purpose of this mission of Perseverance rolling around on Mars is not just to do in the in situ observations that we're making on Mars. We also want to collect samples of the material in the crater and bring those back to Earth so that we can study them in our laboratories here, state-of-the-art laboratories, state-of-the-art instrumentation. Scientists from around the world can put their expertise into studying those samples, and then we can save the samples for decades and have scientists continue the studies. We develop new hypotheses, develop new instruments that can do that science. So that's the main goal here, is to collect these samples that we can eventually bring back to Earth. So what you can see here, this is kind of a complex figure, but you can see the floor of the crater there, and each of these red dots represents a place where we stopped and we took some samples. And each of these little sets of 3 pictures, you can see where the first one on the left, it's where we scraped away the weathering rind on the surface. You can take a look inside the rock. And then we took 2 samples at each one of those red dots. You can see here a real diverse set of rocks collected from this crater floor. We found, surprisingly, exposed volcanic rocks on the surface, igneous rocks exposed on the crater floor. We really expected it would be covered in sedimentary deposits from the lake, and we actually found a couple of places with these igneous rocks that were exposed. Some of them, in some spots, were actually, you could see evidence of aqueous alteration. So they've actually been obviously exposed to water over long periods of time, changing the chemical structure of the rocks themselves. We can use these rocks, the igneous rocks number 1, to date the crater that we believe is around 3.5 billion years old. And so that'll help us get actually an overall time scale for the entire surface of Mars. Right now we have relative time scales, but without actually dating some of these surfaces, we don't know what the absolute time scale is. So we're going to use those igneous rocks to help us date the crater. And then also these rocks that have been aqueously altered, we can use those to help us better understand the environment on Mars when those rocks were present on the surface. We've also collected samples from up here in this river delta. I already said there's a river delta in the crater. This is the main reason we went to this particular spot. The river delta tells us that there was water flowing from a river with a really large catchment area outside the crater, and it brought that water and all of the rocks and sediments that it picked up along the way and then deposited them in this river delta when it flowed in. And this would have been, again, 3.5 billion years ago, about the same time life started to take hold on Earth. We have water, we have energy, we have organic molecules. It's certainly possible that life was also trying to take hold on Mars at the same time it was here on Earth. If it did, this river delta is the absolute perfect spot for those microbial fossils to be preserved in this river delta material. So we've actually collected samples from the mudstone from the lake bed. Those have been collected in some of these here. Each of these ones, I said we've eroded. The 2 pictures on either side are the 2 samples we collected at each one of those locations. We've got mudstones, we've got sandstones, all collected where we potentially could find that evidence of those early microbial fossils when we bring them back to Earth. So this has just been really incredible. We're actually about to deposit one of each of these paired samples on the surface of Mars to keep them as a backup depot of samples that we could go back and collect in the future. If I could go to the next slide, please. But this is the primary plan for how we're going to collect those samples and get them back to Earth. The primary approach is that later in this decade, we are partnering closely with the European Space Agency. The European Space Agency is going to fly the Earth Return Orbiter that you can see in orbit there. It's going to launch first in 2027 and go into orbit at Mars. In 2028, NASA is going to launch the Sample Retrieval Lander. That lander is going to carry with it a rocket, the Mars Ascent Vehicle, and it's going to land on the surface of Mars near Jezero. It's going to hopefully land somewhere near the Perseverance rover. There's Perseverance. By the time the lander gets on the surface, the rover should still be going strong based on performance of the Curiosity rover. We fully expect Perseverance to be healthy and strong. And Perseverance will drive right up to the lander. It's going to carry that other sample from each of those pairs, plus all the other samples it collects over the next several years, drive right up, deposit them into the nose cone of that rocket, and then we launch that into orbit at Mars. It'll release that orbiting sample container, which will then be collected by the orbiter, and then it gets carried back here to Earth again. Hopefully, 2018. This has been an absolutely spectacular mission. In fact, the PI is going to be speaking in the Shoemaker Lecture at about 4:45 today. I encourage people to go see that. But this mission was designed to listen to the heartbeat of Mars. And it's been sitting there on the surface of Mars for 4 years, listening intently. And over that time period, with the seismometers, very, very sensitive seismometers on board, has measured over 1,300 Mars quakes on Mars. And they're saved some of the best ones for last. Last Christmas Eve, December 24th, 2021, there was an impact. An asteroid or a meteorite hit the surface of Mars. It was one of the biggest quakes that we've felt with InSight. And then we were able to go back later with one of our orbiting missions, Mars Reconnaissance Orbiter, and take images of where that meteorite impacted the surface of Mars. And what's so cool about this, not only is it the biggest impact that we saw with InSight, but if you look, this is an image of that impact crater, and you'll see little bits of white around the edge. And what that is actually ice, water ice that was excavated when the meteorite hit. This is important because this is actually the lowest latitude on Mars that we've confirmed the presence of water ice beneath the surface. In the future, when we want to send humans to the surface of Mars, we're going to need to be able to take advantage of resources that are there available. We don't have to bring all of our water, drinking water, and oxygen with us. We also want to try and land those missions as close to the equator as possible. So the fact that we can confirm water ice at lower latitudes is going to be really important. So this is important scientifically and also important as we plan for exploration. The InSight mission down here, you can see her poor little solar arrays are getting covered in dust, and so power generation is diminishing substantially. So fantastic mission, 4 years of great science, but probably only has about another 6 to 8 weeks to go. So stay tuned, but InSight's probably just about done. But what an amazing mission. Next slide, please. All right, let's look ahead. So we're going to look into 2023 and beyond. What's up next in planetary science? If I could have the next slide, please. Right. So this is OSIRIS-REx. This is a mission, let's see, when did it launch? I can't remember the launch date, but it's been out there for quite a while. And a couple years ago, it arrived at Bennu. In fact, I think we did a big press briefing at AGU must have been December 2019, where we talked about the mapping of the surface of Bennu. This is an asteroid about 500 meters across. 500 meters across. And we mapped the surface and identified where we wanted to take a sample from this asteroid. And then sometime during the pandemic, because it's all a blur, I can't tell you what day it was, but it was all a blur, but we did actually touch down and collect a sample. And is this a video? No, it's okay. So when we collected that sample, it was incredible. We've got so much material, we think, in that sample collection canister that we had to button it up fast because we were losing material out of it. So we can't wait to get this canister back on Earth. Same sort of thing with getting the samples back here. We're going to examine them in our laboratories with the best scientists, the best instruments. and what you can start marking your calendar, because next September, on September 24th, 2023, these samples are coming back to Earth, and they're going to land in the Utah desert on that date in September. So we're really getting excited about that sample return. The asteroid, of course, Bennu, really fascinating. It not only from our remote observations, we've confirmed that there's a lot of minerals that appear to have water-bearing minerals, aqueously, that have some kind of water-bearing minerals on there. So that's confirming the delivery of water to places like Earth and other planets in the solar system, that these asteroids can deliver that. It also has evidence that there might be organic molecules and organic minerals on there as well. So getting those samples back here will help us better understand not only the early origins of our solar system, but also understand the delivery of these important building blocks of life that have shown up here on Earth and probably other places in the solar system. And if I could have the next slide, please. One of the other big things coming up in 2023 is going to be a launch of an interesting new mission called Psyche. It's going to launch in October of 2023. This is an important mission that's going to go visit one of the handful, only a small number, less than 10, of these asteroids in our solar system that look like they're made primarily of metal. They're not as rich in carbon as we see in most of the asteroids that we look at, but they have a really strong signature of maybe nickel or iron. So it's possible that this particular asteroid, 16 Psyche, could be the remnant inner core of a protoplanet where they may have been impacted and stripped off the crust and left us with that inner core. If that were the case, this would be our only opportunity to actually see what a core looks like, if that's what it is. It's one hypothesis, and it's going to be an interesting mission of discovery. So that'll be launching next year. Next slide, please. All right. Just want to thank you all for coming here and listening to some of these highlights. We got a million more, but we only have so much time, so I really appreciate you coming by. Please do stay connected, and I'm open for questions. Thank you. How many kilograms of sample are we going to bring back from Mars? And I don't have the answer in kilograms, but what I can tell you is each one of those sample tubes, each of those sample cores, is about the size of your finger or a piece of chalk. So each one is that size, and we're going to bring back, I think, around 30 samples in our sample container. So it's large, a large amount of material by sample return standards. I'm sorry I don't have the kilograms for you. Any other questions? Questions? I'm happy to stand here all day. Go ahead. Say again? Oh, for the Martian human mission. That's a really great, the question is, are there plans for a Martian human mission? So within NASA, we are working on what we call the Moon to Mars strategy. So what that includes is right now a very strong focus on the Artemis program, getting humans to the moon. But at the same time, we are already beginning the planning process for what our strategy is to get the humans to Mars. And that's both technology development, understanding what the science questions are that are going to drive those missions, and starting to think about what that strategy is for doing the human exploration. So we're definitely thinking about it. I don't have specific dates, but the planning is already underway. Absolutely. Yes. Any other questions? Okay. That is a great question. So let me repeat Alex's question. He says, now that DART was successful and we successfully changed the orbit of an asteroid, how quickly could NASA or ESA or JAXA or any agency, how quickly could we develop a spacecraft and get it launched to go out and perform such a mission? I will tell you that right now we're not particularly quick at this sort of thing. So one of the main recommendations in our planetary science decadal survey is they've said one of the next missions for the Planetary Defense Program is to demonstrate a rapid response capability. So that's actually in our decadal as one of our strategies over the coming decade, is to develop that strategy. Do we have spacecraft built and ready to go? Do we just develop a way where we bought parts and we just assemble them when we find out? I think this is going to be part of the studies going on in the coming decade. How do we respond quickly? I'll also mention that in planetary defense, we've demonstrated the ability to change the orbital period of an object, but if we don't know where they are, we can't protect ourselves from them. So the other major mission and activity going on in planetary science, we're developing a mission called the Near Earth Object Surveyor, and its sole job is to find all of those asteroids out there that could be dangerous to Earth. That one, right now, we're hoping to launch that no later than 2028, and that's its sole job. Does the size of the asteroid have a large impact on our ability to change? Yes. We're talking about, conservation of energy and momentum transfer, so absolutely. And again, think about the most important thing we have is time. And the more time we have to prepare, the more effective we can be in our ability, because really tiny changes will add up over a long period of time. So you're absolutely right. Mass is important, but time is the single most important thing, which is, again, why we need to find them soon so that we can go after that. Absolutely. Any other questions? I don't know. I don't know where Steve is. Any more? Steve, how are we? Are we good? All right. All right. I think they're going to take me off here. Thank you all so much for coming.
All right. Perfect. Thank you. All right. Thank you, Dr. Glaze, for that excellent review of 2022 and what we look forward to in 2023. Next, it's my pleasure to invite up to the stage Dr. Kardith Sheikh, Program Scientist in NASA's Science Mission Directorate.
Well, it's my pleasure to talk about astrophysics at the AGU. And as astrophysicists, we are rarely at the AGU, but so my goal here today is to just give you an overview of what our division does in concert, really in the Science Mission Directorate. You heard this excellent talk in planetary science from Lori Glaze, and I'm going to talk to you about what we do in astrophysics. So if we can go to the next slide. So we just finished our decadal survey that Lori mentioned is underway for planetary. And so right now we have been given a certain set of recommendations on how we should execute the astrophysics science going forward. And roughly speaking, we like breaking this down into these sort of 4 categories on how we do our work. You can break the work into strategic missions, and these are flagship missions or probes, which are observatories like the Hubble or the James Webb, as I'll mention in a second. Then a second category of missions we have are PI-led competed missions. So these are what we call the explorers lines, and any of you at a university or at an organization is welcome to come and propose for one of these missions. They can range in size from small missions to medium missions and cost as much as $450 million. A large part of the work we do can be divided into SR&T, or supported research and technology. And the way we interact with much of the community really is through the research and analysis portfolio. And like all of the other divisions, like you've seen for Earth Science, people will put in proposals, we review them, and we fund them to do a variety of research, which I'll mention. A large amount of the work that we also do is in technology development. Most of the astrophysics missions take a lot longer than a typical Earth science mission. And so technology development is really key to making sure that we can get our missions to launch on time and on budget. In addition to that, we also have suborbital payloads, and I'm super excited about that because especially for far infrared and submillimeter wavelengths, balloons are an excellent way for us to do a lot of our science. And then in addition to that, we divide our work into sort of the data archives and the balloon program. You can go to the next slide. Can you hear me okay? Yeah, great. Okay, so as you know, most of the science that we do at NASA or NSF or Department of Energy, etc., is driven by these guiding principles. And astrophysics was in fact one of the first scientific disciplines that started with the decadal survey concept, going back as far as the early 1970s. And what we asked the decadal survey, which is put together by the National Academies of Science to do, is to tell us as a community in a consensus format, what is the science and what is the mission that we should be building and what is the science we should be doing. So if you click on that, the first set of decadal surveys from 1970 to 1990 gave us the first great wave of observatories. So it allowed us to get the Hubble, the Compton Gamma Ray Observatory, the Spitzer Telescope. If you click on it a couple more times here. So the next set of, the next wave is what is giving us the Webb telescope, which you all saw launch, and President Biden revealed the first picture from it, and the Roman telescope, which we're working on now. And then the next, if you click on it one more time, we've just completed the third wave will be started with this decadal survey, the New Worlds, New Horizons survey, which lays out a plan for us to build the next great suite of observatories. And the way astrophysics works is really for us to be able to observe different astrophysical objects in every wavelength possible, from the gamma rays all the way to the radio. And that's why a suite of observatories operating at all different wavelengths is so critical for us. So we're very excited about this survey that just came out, and we're starting to work on it. So we can go to the next slide. Here's the beautiful fleet chart, and it shows you the operating missions, which are in blue here. You can see that we have a number of missions that are in implementation and a number of missions that are in formulation. What's changed dramatically over the last 10 years for astrophysics is the plethora of small missions. 10 years ago, if you'd asked me, could we really do great astrophysics with small missions, we probably would have said no. But this really speaks to the creativity of our scientific community for coming up with really compelling science that we can do on scales of CubeSats and smaller missions. So we're really excited about this fleet. If we go to the next chart, please. Here's another way to look at that fleet. And as I mentioned to you, the way you really do astrophysics, if you're looking at a galaxy or a nebula or black holes, is we want to collect information about that object at all different wavelengths. And what we try to do in the astrophysics division is to have balance in this portfolio across wavelength and across sort of sizes of missions. That gives us the capability to study an object in many, many different ways, to be able to tell what it's made of, what the dynamics of the object are, and what the physical properties and the chemical properties of the object are. We go to the next slide, please. So here are the three big questions that have dominated astrophysics for the last 40 years. I was part of a study in the mid 2013 or 2014, and we worked for 6 months. And after working on it for 6 months to lay out a plan for astrophysics for the next 50 years, we came back with these three themes. And we were all dejected. We said we did all this work, and we've ended up at the same place that's already listed on the astrophysics webpage. But Paul Hertz, who was the director at the same time, he said, folks, you don't have to worry about this. What this really means is these are the enduring questions in astrophysics. We really can just ask these three questions to determine all of the answers in the cosmos. Are we alone? How did galaxies and stars and planets come to be? And how did it all begin? How did the universe begin and evolve? Go to the next slide. Now, back in the 1920s, go ahead and hit the next slide. If we were to ask, when did the study of the universe begin? Well, one of the big changes happened at Palomar Observatory when Edwin Hubble discovered that galaxies were in fact moving away from each other. And we really, the other big discovery was that we were not the only galaxy. The little fuzzy objects that we were seeing with our telescope were really external galaxies. And if you go to the next slide, a key aspect of trying to understand galaxy formation and the universe formation is to understand where are these galaxies, how far away are they? And that's actually not a trivial question. How do you find out on a two-dimensional map of the sky where a particular galaxy is? It's not trivial. So the way we do it is we have a star that might have a known brightness because of the physics that we understand how bright that must be, and we observe it in two different parts of Earth's orbit. And by seeing how the parallax of that object, we can tell how far away it is. Then we take that same Cepheid star and look at it in different parts of our galaxy. And the apparent brightness tells you how much it is dimmed, because the further away it is, the fainter it is. So that tells you kind of how things are in our galaxy. But when you go to more distant galaxies, we have to use spectral lines. And we have to try to understand how much the spectral line has redshifted to really understand how far away that galaxy is. And you may have seen in the news, JWST, the Webb telescope just broke the record for the most distant galaxy just last week. And you're going to see these amazing discoveries come about. Can we go to the next slide, please? Now, this map may look incredibly boring, or like a Monet painting, an impressionist painting, but it really tells you what the universe looked like just a few seconds after the Big Bang, right? This tells you on the scale here is the temperature difference across the universe looked at in microwave wavelengths, and that's in microkelvin. And the fact that the universe is not smooth is the reason you and I are here. If the universe was smooth, nothing would have gravitational overdensities and nothing would collapse. So these little fluctuations in the cosmic microwave background ultimately is what led to formation of structure, ultimately led to the formation of galaxies and clusters of galaxies to give us the universe that we see today. And we are continuously trying to work on the very early universe, now in fact with balloons, to try to remove the foreground dust extinction and really try to capture the first signs of inflation. And then eventually, once we do this with balloons, we will then probably launch a space mission to try to do this even better. Go to the next slide, please. I have a lot of slides, so I'm going to try to go through them quickly. Just an advertisement, we launched the James Webb Space Telescope that you all saw last year, and the next big telescope is going to be the Nancy Grace Roman Space Telescope, which is a successor to Hubble. It can do what Hubble does it will do what Hubble does in one shot in 1/100th the time. It's got the sensitivity and resolution of Hubble, but its field of view is 100 times bigger. So imagine that what Hubble can do in a year, in 100 years, it will do in 1 year. And this is going to be an incredible telescope for us to really do large surveys of the universe, to be able to find those exotic galaxies, stars, and things that are rare and very difficult to find unless you survey a large region of the sky. And the large surveys also help us understand the structure of the universe. And we can relate that back to the cosmic microwave background that I just showed you to try to understand how the universe came to be the way it is today compared to what it was just a few seconds after the Big Bang. So we go to the next slide. So let's ask the next question. Can we go to the next slide again? This is more kind of the physics and chemistry. How do stars form? How do they change? How do they die? How do galaxies form? That entire program we call Cosmic Origins. And really, that's near and dear to my heart because I study galaxies mostly. This is a nice picture. You can see this dark part here that you can't see is because there's dust and molecular gas there that's blocking a newborn star that is at the very center of this little cloud of molecular gas and dust. It's just forming, and as it forms, it shoots out these big jets to conserve angular momentum. These are often called Herbig-Haro jets. And it gives us these beautiful nebula that you've seen. Mostly we only see this in our own Milky Way because we don't have telescopes that can see this in other galaxies. But these are kind of the cradles of the next star systems and the next planetary systems. So that's what we're trying to do with optical telescopes and studying stellar nurseries. Go to the next slide. What we are seeing here is the motion of gas around an extremely red quasar. Now, what's a quasar? Quasar is a term we use for a quasi-stellar object because back in the 50s, I think, when Zwicky first looked at this objects, he thought they looked like a star, but they were a little fuzzy, so he called them quasars. But it turns out that this is really hot gas around a very distant black hole. And by looking at that gas at different wavelengths, we can really understand the composition of the gas around the black hole and how the gas is moving. How the gas is moving then tells us how much mass there is in the black hole. And so these quasars are signposts, very, very distant signposts of what the universe looks like when it was very young. We've seen black holes and quasars at redshifts of 6 and beyond, which means that we've seen them only a few 100 million years after the Big Bang. How they formed, we're still trying to figure out. Go to the next slide, please. Here's a beautiful image of a supernova remnant. So this is a very famous image. This is from NASA's one of our newest X-ray telescopes, XP. And it's showing you the hot gas from an exploded star. And if you click one more time there, what this telescope, this mission is particularly doing that is new, it's really tracing out the magnetic fields. And that's one of the least understood forces, I would say, in the universe. What role does the magnetic field play in either constraining the gas flow or changing the gas flow? And by looking at the polarization of the light, for the XP telescope, we are able to tell how the gas is moving and what the magnetic fields must be. Go to the next slide, please. So this has again been in the news lately. Astrophysics gets a lot of press, so we're very happy. Even though we can't go to distant planets and visit them. You probably saw highlights of stories saying a mega blast of gamma rays came towards the Earth, right? So gamma ray bursts go on and off all the time. They typically happen because either a very, very massive star has exploded, we don't fully understand the physics there, or there's a merger of two stars, neutron stars, and that's what leads to gamma ray bursts. Very, very collimated, high energy gamma rays that are beamed again all over the place. So these are the most energetic events in the universe, and we're trying to understand them now with a lot of our telescopes that look at gamma rays like Fermi and Swift. The next slide. Okay, so this is a question that most excites the average person who may not be really into all the details of galaxies and nebula, is this question, are we alone? Really trying to answer that question in all aspects of the Science Mission Directorate. As you just heard Lori talk about looking for microorganisms on Mars. We are also going to look for them in Europa and other planets in the solar system. But the revolution in astrophysics has been our discovery of planets around other stars. And with that, we are trying to understand and answer this question, are we alone? So if you go to the next slide. So since the launching of the Kepler telescope and the first discovery of a planet around another star, we've discovered over 5,000 planets around nearby stars. Our statistics tell us that almost every single star in the universe probably has a planet around them. That's mind-boggling. And the question is, how many of them have life on them? We don't know the answer. What we do know, and these numbers are apt to change, so, as they say in the stock market, previous performance is not guarantee of future success. But right now, we think about a third of the planets that we have detected are gas giants. Another third are super-Earths. These don't exist in our solar system. They are bigger than the Earth, but smaller than Neptune-sized planets. And then you can see a third of the planets are Neptune-sized planets. So we're now in the process of really figuring out what is the inventory of planets around stars in the Milky Way, and then we extrapolate that to say this is what it must be like elsewhere in the universe. Go to the next slide, please. So this is a movie, if you can click on it. The most common, go back and maybe just hover on the thing. Not able to do it. Okay. You guys will have to do a thought experiment with me. Just imagine the shadow of this thing going across, and you will see that the light from the star will be occulted, and it will dip as that planet goes in front of the star. This technique is called the transit method technique, and it's a very, very powerful technique for detecting planets around nearby stars. This is really kind of what's given us most of those 5,000 planets that you saw listed on the previous slide. And with this technique, if you go to the next slide, we're using a telescope called TESS, the Transiting Exoplanet Satellite, which comes after Kuiper, and the CHEOPS satellite, to really understand the demographics of planetary systems around nearby stars. In this particular incredibly busy slide, I think the only things you should take away are that TESS has confirmed 266 planets. But look at this. Out of the over 1,000 papers that TESS has been used for, 60% have been for general astrophysics, even though this was really launched to be a planet-finding mission, because it's surveying the whole sky and looking for little dips in stars to try to identify what kind of planets are around these systems. The bigger the planet, the bigger the dip. And so it gives you the size of the planets right away. If you had very good signal to noise, by looking at how that light dips, also tells you about what the atmosphere of the planet must be as the light goes through. A thick atmosphere versus a rocky planet. You can imagine if it's a rocky planet, the light will just cut off as soon as it hits the rocky planet. If it's an atmosphere, it will go down slowly. So even looking at how the curve changes tells us something about the planets that are occulting the stars. Go to the next slide, please. Okay, so here is most of the planets we've detected, really, we've not seen a picture. So you've seen all these beautiful images of what life on an external planet must look like, but we've never seen one, right? I mean, we've seen Jupiter and Saturn. Now we can see planets like Jupiter and Saturn around other stars. So here, for example, is a star that's been blocked out. And the image that you see is the James Webb Space Telescope looking at that planet in lots of different filters. And what you can see is that it doesn't quite look exactly the same in each of the filters, right? Because as the wavelength changes, the planet looks slightly different. And that also tells us what that planet must be made up of. And so that's the exciting part. We're just starting this work with JWST, and we will continue to do it. So look for lots of great results to come. If you go to the next slide. So what happens in the future, right? We want to end with what's coming next. This is where we are. Go to the next slide. Of course, all of you have seen and heard about the James Webb Space Telescope, JWST, an incredibly, probably one of the most complex things we've ever built and launched. After we launched it, it had to go over 150 different deployments had to happen as it traveled to its Lagrangian 2 point and unfolded the mirror, unfolded the sunscreens to make it work. And so we couldn't be happier because it is more sensitive and is doing better than specs. And so that just tells you that all the tens of thousands of people who worked on it over 20 years have created something that we've never seen before. And this is just a prelude. And we can already see from the images, if you go to the next image, these things that just make you sit. I mean, don't you all want this in your living room? Just have this big picture to just stare at. There's a big star up above, which is eating away at this molecular cloud. The stars that you see here are in the foreground, and if you were to look at it carefully, there are some red dots which show you very deeply embedded stars. It's like the pillars of light, but this is in the Carina Nebula. Go to the next slide, please. When the first images came out, I was in France at a conference, but I'm sure all of you stayed up and listened to that awful elevator music for a long time before President Biden finally came on TV along with Vice President Kamala Harris and revealed the first images. And then you saw all of the images the following day. And they have made such a huge impact over the world. We've had thousands and thousands of watch parties, and people are... we already have our first science conference on the first results from James Webb next week. So that's how powerful and evocative this telescope has been. You see this here in Times Square. We go to the next slide. And you've probably seen all of these great images that were revealed in that first reveal of the first observations. A foreground cluster lensing all these beautiful background galaxies. Cartwheel Galaxy, the Stephan's Quintet. We already talked about the Carina Nebula. This is something that we've never seen before. And as I said, what we need to do astrophysics is a different pair of eyes. And what James Webb Space Telescope does is it gives us the infrared view of the universe like we've never had before, at the same resolution and better sensitivity than Hubble. So now, all of a sudden, you have a whole new window in the universe, and we should be able to see the first stars and the first galaxies with James Webb Space Telescope. It truly is the successor to Hubble because it's in the infrared. In some ways, it's the true successor to Spitzer in that it allows us to carry on the infrared legacy. We go to the next slide. And then, of course, James Webb doesn't just look at the cosmos, it also looks at things in our solar system. And this view of Jupiter is just amazing. I love all the auroras, diffraction spikes here. You can see the rings and moons of Jupiter. It's just really brilliant. Go to the next slide, please. Lots of online resources. I hope you will all follow at NASA Web, and you'll probably have a news story coming out on Web every week. And I think I'll end there. I think that's my last slide. Yep, and I'm happy to take questions. No time for questions. No damn questions. Sorry.
Yeah.
Okay, I'll stay around.
Yeah. All right, thank you, Dr. Sage, for that wonderful overview. Next, I'd like to invite up Lawrence Friedel, Director of Earth Applied Sciences within NASA's Earth Science Division.
Great. Thank you, Steve, very much. Hello, everyone. It is great to be back at AGU. Oh, my gosh, I've been looking forward to this and being up on the stage. As he said, I'm Lawrence Friedel, and I'm the Director of the Applied Sciences Program. And so what we do is we're helping people apply earth science information in terms of decision making. So it's a matter of helping the application and the use of earth science and remote sensing to support decision making activities. And really it's helping people do that, helping organizations do that is really what drives us in the Applied Sciences Program. And so we make investments in terms of funding and programmatic investments such as training activities and investments in applied research and technical sorts of things to really help this connection between decision making and the use of science. And so what we mean by sort of decision making is we're going to be exploring that today. And so you can see behind me this Hollywood squares of individuals, and we're going to be introducing you to three of the people that are shown up here. And we're also going to be looking at three different types of decisions in how we're using earth science information to do that. And so we're first going to be going to Carly McClellan. And so if we can go to the next slide. And so we're going to be going to the Navajo Nation. And so Carly grew up on the Navajo Nation. And so he grew up there. He went off to college, got a degree, actually worked at a car mechanic for a while. And then he came back and he got involved with something called the DEVELOP program. There's actually a lot more information about DEVELOP. It's a program that we have to help young professionals get involved with geospatial information. So that's satellite data and other types of information. And so he got involved with a project related to the Navajo Nation. So let me back up for a second. If you're not aware, the Navajo Nation is in the northeast corner of Arizona, and it covers an area of about 70,000 square kilometers. That's about the size of West Virginia. It's a very arid area, a very arid region, and so they have persistent drought. But the drought is really variable across this very, really large area. And they have a number of rain gauges, but they don't really capture the variability of the drought that exists across this really, really large region. You can go to the next slide. And so Carly, in this DEVELOP project, worked in terms of using some of the satellite data as well as the rain gauges that the Navajo Nation had to sort of do an initial effort to see whether the satellite data could help. And what they discovered was that, yes, it did, but at the end of the project, Carly sort of said, yeah, it's providing some interesting information, but it's really hard to use. And I have to say, in the Applied Sciences Program, that is exactly the type of feedback that we like getting. It's someone who essentially understands how this is going to be used in a real decision-making context and is really interested in helping it make it better. Because after all, it's not about just helping people find the data. It's really about helping people put that data to work for use and improving what they're doing with that. And so what we decided to do was we expanded the project. We brought in other people. And so Carly here is pictured with Amber McCullum. So Amber is an earth science researcher at NASA. The two of them expanded the project, worked with a bunch of other people to bring them in, and they combined, here we can go to the next slide, and they combined information from the rain gauges along with satellite data and some climate modeling activities. So the information that they had from the satellites was things like land surface temperature from Landsat and MODIS and VIIRS. They did precipitation data from GPM and historical information from TRIM. And then they also had these climate modeling products and they brought this together into something called the Drought Severity Evaluation Tool. And you're sort of seeing an aspect of this right here. And so this information really helped with resource allocation decisions that the Navajo Nation has. And so before this tool, when there was a drought, the Navajo Nation had some drought relief funds, but what they were doing is they were providing the money and the funds equally across all 110 chapters. After they had this tool, informed by the satellite data and the climate modeling sorts of things, they were able to pinpoint exactly which places were experiencing drought more than the others. So they could distribute these drought relief funds much more equitably based on the impacts that were going on in the different chapters. Today, Carly McClellan is the senior hydrologist at the Department of Water Resources in the Navajo Nation. He's still in contact with Amber. They're still looking at additional things that they can be doing, as well as other projects that they might be pursuing. So that was an example looking at uses of earth science information to support resource allocation decisions. The next decision that we want to explore is the development of early warning systems to support decisions for people's planning in anticipation of some event. And to do that, we're going to go to Puerto Rico. So next slide. And we're going to introduce you to Pablo Mendez Lazaro. He's with the University of Puerto Rico's Medical Center. And what he did was he helped set up an early warning system for Saharan dust. And you can sort of see, this is one day, here's the next day. This is a huge issue for Puerto Rico at times, in periodic times. Now, when you think of Puerto Rico, you don't typically think, well, you might think of beaches and very nice sandy beaches, but you probably don't necessarily think of Saharan dust. But like I said, it's something that they have to deal with periodically. Next slide. And part of it is because we live on this integrated Earth system. And you can sort of see that dust and Saharan dust and sand gets entrained, travels 10,000 kilometers to the west, and gets deposited in the Caribbean area. And this is not just sort of a nuisance, but the dust really has health effects. And so it can get into the lungs, and really it's causing irritation, and even more than that, there's respiratory mortality associated with the dust that's coming over from Saharan quite often. Next slide. And so what they did was actually, can we go back one? I'm sorry. So they developed this early warning system, and they helped provide information. So they used information from MODIS and VIIRS, the aerosol optical depth, and other information about particulate matter in order to develop this early warning system. And that was getting information out to hospitals and local officials, and even to television stations to help get the word out. And by doing that, individuals could understand when they needed to stay inside, when they needed to curtail certain activities, when they needed to take their medicine, and things like that. And so really, this is an example of Earth observations informing early warning systems to help individuals understand what actions that they needed to take to keep themselves safe. So the third decision example that we want to explore today is more related to planning decisions, and especially planning for sustainability. And to do that, we're going to go to Mongolia and the world of high fashion. Next slide. And here I want to introduce you to Sergey. So Sergey is a goat herder in the Mongolian Gobi Desert. Now, Mongolia and Mongolian goats produce some of the highest quality cashmere wool in the world. And there has been really strong increasing demand over the last 30 years for this cashmere wool. But the growth in the herds of these goats has really, really impacted the environment. And it's really created some threats to the native grasslands that are there. And that is going to be impacting the sustainability, which is going to be impacting the supply chain, and that essentially is going to be impacting the livelihoods of the goat herding community, like Nergay, and their families, as well as their the broader communities. So, and climate change is also making things even worse. And so, in the winters, there's more extreme temperatures, and the summers are getting hotter, as well as there's desertification of some of the grasslands. And so combining, there's real threats to the sustainability of this. So a group of organizations got together to form a collaboration, something called the Sustainable Kashmir Project. And so this involved conservation groups like the World Conservation Society. It involved fashion companies like Keurig, who is the holding company for brands like Gucci and Yves Saint Laurent. And it involved earth scientists. Some of the people that we sponsored are here. On the left-hand side is Cindy Schmidt with NASA, NASA Earth Science, and Becky Chaplin Kramer, who was formerly with the University of Minnesota as well as Stanford University. They teamed up, and most importantly on the team was Sergey. So Sergey was that goat herder. And what we've learned in our applied sciences projects is involving the people that are going to be actually making those decisions is the most important part. We need to be doing the co-development, the co-design of these different projects to make sure that the adoption at the end is really what's going to be there. And so what they did was they combined a whole bunch of different earth science information, land information, they looked at climate, and they looked at weather patterns and a number of sorts of things to do this analysis. And so they were looking at what were some of the practices about the grazing, and they were looking at the impacts of climate and weather and a number of other factors. And what they found was that the climate and the weather impacts pose the greatest threat to the long-term sustainability, but that the goat herders can't make those sorts of decisions. What the goat herders could control was where they could graze and how long they would graze there. And that's the information from these tools that really, really help them out, to help them understand where, as well as to help them understand how long they should be there. And one of the great things about this was that Sergey came back and he just had all sorts of praise for this tool. And so this was a great example of using earth science information to do planning decisions for people like Nergey, and others. And so I've showcased these three. Here's sort of another example related to it. We can go to the next slide. And so I've shown you these three people, three different ethnicities, three decision types. And it's been a fantastic sort of experience in working with each one of them to sort of see in the different context how earth science gets used. But what we really want to understand is what other ideas are out there. So these three examples are just three of many. But we're always looking for what's that next example. So what we really want to do is hear from you, what you all are interested in. Who are you working with? Because right now we showcase to some. What we'd like to do at next year's AGU or the one after that is we'd like to have you up here. We'd like to showcase you or showcase your partner up here. Quite frankly, I'd like to be in the audience and have you up here giving the talk, talking about your partner and what earth science information that you all used. Now, if you're interested in getting involved in earth science applications, there's many of us here from Applied Sciences. You come talk to me. There's some people out in the audience who work with earth science applications. You can please talk with them. We have a table right over here that talks about develop, and we actually even have a guidebook on how to do earth science applications. I encourage you to do that. With that, I just wanted to say thank you very much for your attention. Really appreciate it. Please come up and see me. I'm here through Thursday evening if you got interested in ideas about earth science applications. So thank you for your attention. Thank you also to the Hyperwall team. Thank you very much for the Hyperwall team and all that. We do have time for questions if there are any. Great. Thank you so much, everyone. Have a great week at AGU.
All right, thanks, Lawrence, for that great talk on applied sciences. We are waiting on the arrival of our next speaker. She is literally running from a session to get here, Dr. Dahlia Kirschbaum. So we're just going to take a quick breather and wait for her to arrive. Thank you.
Did you find it?
Yeah, 117.
4117? Got it.
Yours we said at 44128 is the whole.
SDR.
I can ask you to go to it. There you go.
Okay. All right. Hello, everybody. I'm going to be a filler today as we're waiting for Dahlia Kirschbaum, the Director of Earth Science at Goddard Space Flight Center, to get here. In the meantime, my name is Alex Young. I'm a heliophysicist at Goddard Space Flight Center, Associate Director for Science. And so I just wanted to show you a little bit, a flavor for what you'll see later when we have Nikki Fox from Heliophysics come. She'll be talking about the sun and its influence on everything in the solar system. And we start with the sun. So what I'm showing you here is images from the Solar Dynamics Observatory, or SDO. So if you look right here, this kind of yellowy image, this is what you might be familiar with the sun, kind of this sort of boring yellow ball. If you have the right kind of protective eyewear, sometimes you'll see these dark areas. These are called sunspots. But if we then take a bunch of telescopes, launch them into space, and put them above the atmosphere, we're able to see many other wavelengths of light, especially ones that can't make it to the ground. Those in particular would be UV, extreme ultraviolet, and also X-ray. So looking at the sun in visible light, we're seeing the lower layer of the sun's atmosphere called the photosphere. And it has a temperature of about 10,000 degrees Celsius or so. But if we start looking at more and more energetic light, UV, extreme ultraviolet, all the way to X-ray, we see higher and higher temperatures. So as we move into ultraviolet, we see temperatures in 20,000 or more degrees. As we get here in extreme ultraviolet, we're seeing temperatures around 80,000 degrees. And by the time we get all the way over here in the most extreme ultraviolet, almost on the level of X-ray, we're looking at 2 to 3 million degrees. So that's one of the great excitements about the sun. And I'm going to pass it on to Dahlia to talk about the Earth.
Okay. Hi, everyone. All right, so who's already ran a marathon today? Because I have. All right, my name is Dahlia Kirschbaum. I am the Director of Earth Sciences at NASA's Goddard Space Flight Center, and I am going to give a bit of a talk of how we understand our Earth from the atmosphere, from the surface, from the subsurface, across our oceans, and our land. So NASA has the largest Earth system science fleet orbiting our Earth with its eyes pointed down at Earth. And so I want to talk a little bit about how we are understanding our climate, our Earth's changing systems, and what we are learning in the process, along with our both domestic and international communities. So first, looking at something that's very important in sea surface height, excuse me. So the continuity of observations to understand long-term change in climate is fundamental to understanding the Earth as a system. So this is an example of sea surface height. And these are the missions in the queue and that are flown that are highlighting the importance of providing that continuity of observations for sea surface height. What you see is they're not all consistent around the world, right? Height differs in different places. Understanding the flows of the ocean to give us that height is fundamental to our understanding of ocean circulation and how heat is trapped. So the most recent satellite, Sentinel-6B, Michael Freilich, is helping us to understand, or Sentinel-6, and then in the queue is SWOT, the Surface Water Ocean Topography Mission, helping to understand the continuity of surface height of our water, understanding hydrology, as well as ocean dynamics. And we're really excited about the SWOT launch. That's why I'm here, because Karen St. Germain is on her way to the launch of SWOT, which will happen in just a couple days. So moving on to understand how NASA is observing our climate system. One way to start in the atmosphere, we do this by understanding the distribution of greenhouse gases such as carbon dioxide. And so what you'll see here, this is a model from the Global Modeling and Assimilation Office that helps to highlight the distribution and time frame of CO2 emissions. Now, NASA has prioritized the understanding of greenhouse gases both in the past and into future missions with a focus on the Earth System Explorer concept to understand and advance our understanding of greenhouse gases. And as you see here, as we move through time, these CO2 measurements, there are clear sources of this type of CO2 emissions, and our goal is to understand the location, the distribution, and how it moves across our Earth. If you go to another greenhouse gas, methane, we can understand, so methane is an incredibly potent greenhouse gas. And so we have observations, such as with EMIT and other sources, to help us understand the sources and sinks of methane, which sources include fossil fuels and other agricultural and industry areas. And so by being able to understand the location and distribution of sources of methane and then model that as a global system, it helps us better understand where in the atmosphere we are holding this distribution of methane and ultimately how we can mitigate it. So moving on. Now, all of this heat and energy that we have trapped in the atmosphere, most of it goes into the oceans. So what we have here, this is showing ocean circulation and then the ocean heat content. And so understanding how the ocean is going to be absorbing that heat, and it doesn't stay in one place, how it transports over locations is critical to understanding that dynamic in how that heat is moving around our ocean, how it's absorbed, and how it may impact the future climate signals. And so when you put that all together, we can start to understand the warming with ocean circulation, and we need to understand our glacial regions, right? So this is the view of changing Arctic ice sea loss, right? So over time, we've had a significant decrease in the thickness of sea ice over time. And understanding the albedo, the feedback effects from the sea ice, is incredibly important to understanding the Earth's radiation budget. But it also starts to speak of different security issues, such as navigability of the Arctic. And so we have missions such as ISAT-2 and other field-borne campaigns that allow us to understand those changing signatures over time. And so in addition to that, we can start to understand not only the density of ice change, but we can look at the mass loss from ice sheets. So as the ocean warms, it creates warming pockets which accelerate ice melting. Okay, so over time, what you see here is from the GRACE and GRACE follow-on missions. And here you see changes in ice mass over time. And this helps us to understand the contribution to sea level rise, as well as to other more local impacts, such as changing dynamics of Greenland here. And so by being able to have these continuous observations of sea ice, we're able to look at this dynamic from space using our constellation of satellites incorporated with models. So speaking of models, so our one of the key areas in being able to understand the Earth as a system is taking all the observations that we've talked about and more and bringing them into models to understand how things have performed in the past, to understand and observe the present so we can better predict the future. And so what you see here on the top is actually changing temperature in the stratosphere. This is the lower stratosphere, and this is the surface. So this is surface temperature change, and this is ocean heat content. But the thing, I know it's busy, but the thing that I like about this graphic is that the observations are shown in white, natural drivers are shown in green, human drivers in red, and combined in blue. So by being able to better understand the past and track what is natural and what is human and connect those, we are able to better measure and model how things are changing into the future and understand the real drivers of what is causing our climate to warm and to change. So you can see that the observations track very closely with the combination of natural and human interactions. Okay, so in addition to understanding the state of our climate, we also need to understand the impacts. How is that manifesting with us on Earth? And that's where my research area is more focused. So by being able to understand the mean sea level change, it has huge implications for coastal regions. And so things such as sunny day flooding, like in Miami, every day there's flooding, is a result of these changes in mean sea level locally. In addition, we have extreme events like storms, and that accelerates the storm surge, that intensifies that. So some of the tropical cyclone impacts are even more exacerbated because of this changes in sea level rise. Okay. But in addition to understanding how our extremes are, we need to understand how they're manifested in the extremes, both drought and precipitation. And so what you have here is actually the changes, the differences from normal in where areas are getting wetter. This is the anomalies in near real time, and where some of these areas are getting drier. Now we know in the changing climate system, we're going to have more extreme droughts, more extreme floods. And the importance of what we do is to harness all of these measurements into models to better predict the local impacts that we may have. And so by being able to understand extreme events, such as flooding, we have satellite data that can help us pull together the observations of sea surface temperature, where we may have storms that accelerate and intensify, which is a huge area of research, what causes storms to intensify where, and then allow us to couple that when these storms make landfall with things like flooding, to be able to, for example, from Landsat, understand these changes over time and to build up these inventories to test new models. So one way in which we're extending these observations and connecting them to societal applications is with things like the Global Precipitation Measurement Mission. So this is Hurricane Ida, and with GPM measurements, we can see through storms. It allows us to understand the actual physical distribution of precipitation and storms from the surface to the top of the atmosphere. We can see snow at the top of these storms, and these hot towers, these huge convective spikes, allow us to understand when storms are intensifying. And actually GPM got this image right as Hurricane Ida was intensifying and about to hit New Orleans. So giving this talk in New Orleans last year was incredibly topical. But in addition to understanding the storms themselves, we need to understand their impacts to society. So this is an image from SUMI-NPP, which is a NASA NOAA satellite. And this is a view of the night lights before and after Hurricane Ida made landfall, just a couple days after landfall. And so by being able to connect the night lights and the loss of light from these major storms around the world, we are able to get that information to emergency responders to know where they need to address community needs, where to put in generators, and work with the emergency response community through our disasters program to enable more information to be used to make effective decisions. So another way in which we can understand the impacts is through agriculture. And this is an area that NASA is really hoping to improve our understanding of soil moisture from missions such as the Soil Moisture Active Passive mission, and work directly with organizations that work with farmers to understand how to better relate what we are observing both in real time and in the past and future to changes in agriculture. We have great consortiums working on this, such as NASA Harvest, as well as many other initiatives working with our federal partners, USDA and others, to better understand and relate these processes to the bigger Earth system impacts. And so if we go forward, so how do we understand that in the future? Well, some new work by a scientist at NASA GISS has been able to understand and incorporate climate models in projections with crop models to look at the future of maize yields and wheat production in different areas of the world. And so as things change, you'll see that some areas are okay. This is the percent change. Red is negative change, and green is more productivity. And you see that there are changing locations where agricultural yields are going to be more pronounced. And it's not just about food. There's a lot of our different industries that rely on maize and on wheat for things like glue or things that enable our everyday lives. And another part of this new study is that actually the protein content of some of these crops are going to change because of climate. And that is something that we are just starting to learn about. But the protein in rice is going to change because of climate change. So working with the crop modelers, working with our climate scientists together as an integrated system, we can start to better understand these impacts going forward and ultimately have more information to enable and mitigate decisions. or mitigate decisions to help. Another area in which NASA is actively engaged is fires. So the Fire Sense effort is a focus across NASA and with other federal partners across the world to understand how fires are changing. We know that the fires of today are going to be different in the future. There's going to be more extreme fire weather. We're already seeing that every year. And so by being able to have radiative heat index, so radiative fire index such as this, allowing us to understand where fires are initiating, but then allow us to propagate those to see how they impact the landscape before, during, and after their occurrence is important. And I literally just came from a session where somebody was talking about how precipitation extremes may be changing the impact of post-fire debris flows in fire regimes. And so looking at those synergies is why we do what we do and why the community it's important to engage together on these important topics. All right, so how do we do this? Well, there's a lot of data. So this we call the light bright chart, but the point of it is that we have 6 million data points every 6 hours going into some of our climate models. Okay, and it's only increasing exponentially from there. So how do we harness this information from satellites, from aircraft, and beyond to really better understand and use this information to understand our Earth as an integrated system? Well, we do this with missions such as SWAT. We're excited about how we can fill gaps in the record. SWAT will be the first global survey of our Earth's elevation of water, and that's launching later this week. Using interferometry, we are able to understand the height of our lakes and our rivers and high-resolution aspects of our ocean, and that will be critical for understanding our global water balance, our hydrology, and the impacts on our freshwater resources. And we are also doing this as part, and I'm sorry, this is the altimetry. So this is an example of the past, present, and future of what we will glean from this type of information from SWAT, which is a collaboration with NASA and our partners at CNES in France, as well as contributions from the UK and Canada. So going forward, we are able to look not only at our Earth ocean height, but we can also look at the productivity of our oceans. So the PACE satellite is going to be launched in January of 2024 and enable us to understand ocean color like never before. We are advancing our understanding of the aerosols and the impact that they have with our oceans, and then the productivity of our oceans in about 100 and so different bands, allowing us to understand the characteristics of our ocean and continue that important record of ocean health, which is a fundamental signature of climate change as well. Okay. So going forward, all of those satellites are leading up to the Earth System Observatory. So as part of the 2017 Decadal Survey, there are 5 designated observables. There are clouds, convection, and precipitation, aerosols, which is looking at the distribution of dust and smoke around our planet, the changes in surface, in mass change, large-scale redistributions of our surface, as well as certain surface deformation and change, and finally, Earth's surface and ecosystems from surface biology and geology. So this observatory, which we've been talking about and you'll hear about at the town hall, which is on Thursday at noon, or 12:45, allow us to understand a new vision for Earth science, how we can create integrated approaches to measure different aspects of our system, but then connect them directly to societal benefits to inform the next generation of how we see our Earth and how we can make impacts to mitigate the impacts of climate change going forward. So finally, I want to close with another activity that's evolving, and this is very much in process, and that's the Earth Action Strategy. And so how do we take all of those types of new observations along with our ability to connect them with tools and models to come up with solutions? And so this is part of a new effort to better understand how we can connect the Earth system and work with our federal partners in around the world to better impart change for actionable solutions to our climate. Go ahead. And with that, I will close, and I'm happy to bring any of the program managers up that that would like to answer any hard questions. Thank you.
Awesome job.
difficult to show that last slide.
All right, thanks, Dahlia. Okay, and we're going to conclude our set of Hyperwall Talks today with our Division Director of Heliophysics from NASA's Science Mission Director, Dr. Nikki Fox.
Thank you. Thank you so much. I have got the most exciting talk today because I get to tell you about something that is totally fun. It is the Heliophysics Big Year, and this is going to be a global celebration that everyone can take part in. So we go to the next chart, please. Next chart. Thank you. And so this is our beautiful logo. This is the Heliophysics Big Year. And why do we study heliophysics? Heliophysics is really important. It is the study of the star that we all live with. That star, as you may know, at December of 2019, kicked off the new solar cycle. So we are currently moving up towards the next solar maximum that will happen at the end of 24 or the beginning of 25. And so this is a really great opportunity for us to study our star in a way that we've never been able to do. And as you'll see in a minute, we've got a ton of really exciting activities and a ton of really exciting missions that we're going to use to study it. So we'll go to the next chart. Thanks. So the sun touches everything is really our motto for the Heliophysics Big Year. It is our star. It is completely, we wouldn't be here without our star. We often hear it described as an ordinary star, but that's really not fair. It may be an ordinary star, but it's the only star that we know that actually sustains life on our planet. And so it is the only star right now that we know that has that kind of awesome responsibility. And so it may be an ordinary star, but to us, it is an extraordinary, ordinary star. And so it's really, really important that we study it. And through the Heliophysics Big Year, we will study not just the star, but we'll also look at the impact that the star has on us here, physically, emotionally, for some people, even spiritually. So it's a great opportunity for us in this Heliophysics Big Year. And so I just wanted to if we can go to the next one, you'll see a really cool little image that was taken by the Solar Dynamics Observatory. This image, actually, when it was released, the image went viral, and you may have even seen it on Saturday Night Live. It is our very happy, very jolly star. And it just shows how images that we have from our amazing missions here at NASA can really capture the public imagination. And so we want to build on the interest that we see with these incredible images. It's just cool, isn't it? Really, it's a happy sun. Everyone in heliophysics is happy. We have a happy star. Next chart. And so through the Heliophysics Big Year, we'll kind of bring together a number of different activities. So I'll talk about the eclipses in a minute. The eclipses obviously are a great opportunity to bring people together. It's an experience that you have. It's kind of a unifying experience where everybody sees the same thing at the same time. But also we're going to be focusing on the science that we do. We're going to be finding ways to kind of meld the really cool cutting-edge science we do in heliophysics with sort of some of the more softer science, some of the sort of more humanitarian aspects. We also want to focus on all the exciting things that we're doing with our missions, whether it's a mission in space or whether it's a mission that is getting ready to go to space. There are lots of great milestones and lots of things that we want to tell and educate the public about. And then citizen science. We want to really involve, we want to open up heliophysics science to more than just our PhD scientists, but to really go, and you don't need a science degree to study. You just need to be really passionate and really curious. And we want to help actually implement that for people. Next chart. So the big year will kick off in 2023, in October of 2023, when we will actually be treated to an amazing view. We will actually see an annular solar eclipse, and it will be visible from here in the US. An annular eclipse is a beautiful sight. It looks like a ring of fire around the sun. You will need your eclipse glasses. I need to do my public safety because I see my people down there. Yep, you have to, if you're looking at an annular eclipse, you must wear your glasses. So we will kick it off in October of 2023. It will then continue, and it will take us into the total solar eclipse, which is in April of 2024. For that, You have to keep your glasses on until totality, but at that point, take them out and look at that beautiful corona. This is a fabulous example to do that. I'll also note the incredible science that can be done during an eclipse. And as I see Laurie Glaze, the planetary over there, you can see Venus and Mercury during a total solar eclipse. So you can see the planets and you can see the kind of day sky for just those few moments as we see totality. Next chart, please. The other thing that's really exciting for us is we will be on the upswing on our way to solar maximum. So the solar maximum is already the sun is more active than was originally predicted. The activity is ramping up very, very quickly. And so we are seeing a lot more space weather and a lot more solar events happening all the time now. And so that gives us a great opportunity to do amazing science. As we see more and more of these events, we can actually start to do some sort of campaign events where we see something happen on the sun, and then everybody all over the world puts their data together to allow us to really study the impact of our star here on our planet. So some really, really, really great stuff that we can do on the way up to solar maximum. And then the heliophysics big year finishes with the final perihelion configuration for Parker Solar Probe. So we will have just done the 7th Venus flyby right ahead of this. And so it's a Christmas present. Christmas Eve, Parker Solar Probe will be within 10 solar radii of the sun's surface. And so for us, that really sort of ushers in a whole new era of science. We are finally in a region that people have dreamed about traveling to for over 60 years. And in December of 2024, we will finally be there. And so that sort of will tie off the end of the big year. But for us, it's not the end. It's kind of the beginning. It is the springboard of all of the great stuff that we have coming up in 2025. Many of you sitting here are associated with missions, and those missions most likely are launching in 25 and 26. So it sounds like it's a long way away, but for anyone on a mission team, it's just right around the corner. Next chart. Thanks. So it also is a really great opportunity to actually showcase everything that we have in the heliophysics portfolio. And so here you're just going to see some of the really nice missions that are up. This is a really nice graphic that actually I think really does a good job of highlighting the vast space that we have to cover with heliophysics. We go all the way from the center of the sun, we go all the way really close to the sun with Parker Solar Probe, and then we go all the way out into interstellar space with our Voyagers, and we study everything in between. So we're really proud of these incredible missions that have been bringing us data for years and years. So it's very easy to get excited by the latest bright shiny mission, but the bedrock of heliophysics is the missions that have given us the really long baseline measurements, things like timed MMS, Themis, ICON, these wonderful missions that have been going that continue to bring us great data. And of course, I would be remiss if I did not note that our Voyagers celebrated their 45th birthday, which means they're older than most of you. And so they are now out. They are truly our interstellar travelers out in the interstellar medium. We'll go to the next chart. Thanks. And so it also gives us a great opportunity to highlight all the amazing work and all the new technology that is represented by our new Helio fleet. And so, as I noted, we will really start launching all of these kind of with a vengeance in 2025. The IMAP mission will go to the L1 point, and thank you for the cheer. That will go to the L1 point, and it will study not just everything that is coming to that spacecraft from the sun. It will also look out and image the sort of fragile boundary that separates the sun's atmosphere from interstellar space. And so IMAP doing an incredible job to really help us sort of look at the shape of our place in space. IMAP will also carry with it the newly named, this is actually the first time I've done this in public, this is great, so the newly named Carruthers Geocorona Observatory. So yes, we renamed that mission last week. It was the mission formerly known as GLIDE. We are delighted that we were able to rename that mission to honor George Carruthers, who many of you will know actually built the telescope that took the first images of the Earth's geocorona and kind of let us know how big the atmosphere around our planet is. And so Carruthers Geocorona Observatory for the very first time on the fleet chart. We will also be doing a lot of these other missions will be going. I don't have time to go into all of them, but Punch will be looking, sort of partnering with Parker Solar Probe and Solar Orbiter, looking down in the deep corona to work out how solar storms really start. And Tracers will be going to kind of look at the coupling between the magnetosphere and the ionosphere in the Earth's northern hemisphere cusp. And I see you, or will be launching in 2025 to go up to study gravity waves, looking down from the International Space Station. And of course, GDC. Geospace Dynamics Constellation, it will be going up as well very soon. We are in the final throes of selecting the instruments for that, so early next year we will have our full science team together. I'm really excited about all the stuff that GDC is going to do. If you would like to know more about GDC, there is a town hall on Thursday at 1:45. I should also note, if you would like to know more about these missions, the awesome Nicole Rail will be up here on Wednesday at 3:05, I think. And where's Kelly? Kelly Corrick will be telling everybody about the eclipse here tomorrow at 3:50. So lots of exciting stuff happening up here on the hyperwall for heliophysics. Next chart, please. All right, and it would not be complete if I did not talk about the incredible work that we have kind of from our low-cost access to space program. All of these things will be actually taking part in the eclipse as well. We will have sounding rockets that are dedicated to studying the eclipse, one for each of the eclipses, one going up from White Sands. We'll be looking at the annular eclipse, and then a second one going from Wallops will be studying the total solar eclipse. So really excited again to include our sounding rockets in our science as well as in the eclipse studies. Scientific ballooning, we really enjoy being able to put our science payloads on balloons as well. And of course, many of you will know that the eclipse also provides an amazing time to do ballooning experiments. And so the balloon program, also a big part of our portfolio. And then CubeSats and SmallSats. We look at these sort of in many different ways. All of these programs allow us to sort of fly technology maybe that hasn't been flown before and qualify it. They allow us to get early career, maybe first-time PIs to get in and get that experience. And they also do really cutting-edge science. And that is true for all of these. For our sounding rocket, for our small sats and CubeSats, not only do we see those in our low-cost access to space, but we also now see them in our large missions. And so we have a new mission that was recently selected called Helioswarm, and that is 9 spacecraft, one sort of node in the center and 8 small spacecraft that will swarm around it, studying turbulence in the solar wind. And it's just so great to see something that started off more as an educational aspect, really now in the main portfolio for heliophysics. Next chart. And I want to kind of start to wrap up by, just highlighting what we do in our RNA program, because all the missions, all the technology, they're all great, but they don't mean anything unless you have a really good research program underneath. And so we have had some tremendous successes in our RNA program in the heliophysics division. It actually I think we had a workshop last year. It was Helio 2050, and it was a chance to bring people from all different aspects, all different areas of heliophysics, to have discussions together on the future of heliophysics. And so, they were just tremendous discussions that we had. I know that most of those discussions actually fueled white papers that were recently delivered to our heliophysics decadal when it was kicked off earlier this year. We had a tremendous response from the community. Thank you, thank you, thank you. I asked and you delivered. 493 white papers were submitted to the Helio Decadal. That is almost twice the number that was submitted to the last decadal. So really, really great job. The other thing I've really noticed with heliophysics is how we are kind of broadening the science. So it's not just heliophysics at the sun and the earth, it's also heliophysics type science at other planets in our solar system, at other stars and other planets in other stellar systems. And so I think it just really speaks volumes to the power of what you can do with heliophysics. Next chart. And I will... Yes, so citizen science, I mentioned the importance of citizen science. In fact, the term big year actually is a citizen science term. It comes from birding. And so in the birding world, during a big year, birders are challenged to see as many different species of birds as they can in that year. For the heliophysics big year, we are challenging you to see and experience as many sun-related activities as you can, hopefully in new ways that you've never done before. And so we'll go to the next chart. And some of the ways that you can do that are to get involved with our citizen science program. So we have the Aurorasaurus is one really great way. If maybe you don't like the sun, that's not your thing. The Aurora is really spectacular. Go find one of those. We also have the brand new Sprite-tacular program, which is focusing not just on chasing elusive sprites, but also capturing them on film. So please get involved. This, as I said at the beginning, you don't need a degree, you just need passion. Last chart. Thanks. And so the sun is going to have a huge year. In fact, the year is so great, it is a big year. It starts in October and it ends in December of the following year. It's a big year. In that year, we want you to bring your joy and your curiosity with you. We want you to go and experience eclipses. We want you to see aurora. We want you to join in with citizen science, and we want you to get really excited about everything heliophysics. The solar maximum is coming, and it's just opening up an amazing opportunity for us to do incredible science. Last chart. And so with that, I will just leave you with the website, very important. Please, you can, if you click on the Q code over here, you can get all the information. Follow us, do check out what's going on the website. Follow us on social media, and just make the sun a really, really big year. And I will finish with my favorite line, which is, it is totally a great time to be a heliophysicist. Thank you.
Good job. All right, folks, thanks very much for coming. This concludes our formal Hyperwall presentation set tonight. But, you know, of course, we're open for another hour or so, so please feel free to continue browsing around the NASA exhibit. There is lots of science to discover while you're here. Thank you. And then I need to make an announcement for heliophysics missions people. Please come to the stage for a group